All right, welcome. Today we're putting on our senior aerospace architect hats. We are going to define the very heart of future flight, the battery management system for an eVTOL aircraft. And let's be clear, this isn't just about watching a battery's charge. This is about architecting the life support system for a brand new era in aviation.
So where do we even begin? Well, to really understand the fundamental challenge we're facing up in the sky, we actually have to start right here on the ground with something we all know. So take a look at this. On the left, you've got a standard electric car. If its battery system senses a major problem, its job is simple: fail-safe. It tells the driver, cuts the power, and you pull over to the shoulder. Easy enough. But on the right, well, that's a different story. High above a city, there is no shoulder. There's simply no place to land. And that one simple fact forces a massive shift in design philosophy. We have to move from fail-safe to something called fail-operational. The system can't just shut down safely. No, it must keep working, even when parts of it have failed, to absolutely guarantee the aircraft can get to a safe landing spot. This isn't just an upgrade. We are in a completely different engineering universe now. And when you look at the raw performance demands, this difference becomes even more stark. Think about it. An EV needs a burst of peak power for maybe 10 seconds to merge onto a highway. An eVTOL needs that same peak power for up to 2 minutes just to get off the ground. That is a whole other level of stress. And we see the same thing with usage cycles. All of it built on that fundamental shift to being fail-operational. So this whole fail-operational idea, it's not just a preference or a nice to have. It is a hard and fast rule, and it's driven by one of the most demanding safety standards in all of engineering. This is the number, 1 × 10⁻⁹. This is the required probability of a catastrophic failure per flight hour. It means a failure is so unlikely, you'd expect it to happen less than once in a billion hours of flight. It's a number that's it's almost impossible to wrap your head around. And this quote right here just nails it. This isn't some aspirational goal. This is the absolute, non-negotiable price of admission. If you cannot prove your system meets the standard, you don't get certified. You don't fly. Period. So how on earth do you engineer for 1 in a billion reliability? Well, you don't just cross your fingers. You use a structured top-down approach. We're going to build what I call a pyramid of safety, where each layer is designed to handle a different kind of risk, and altogether, they cover all the bases. So here it is, our safety pyramid. You can see how each layer is distinct, right? But you put them all together and they cover everything. We're talking about the physical environment, the logic of the electronics, and all the way down to the battery chemistry itself. Okay, let's start at the bottom. The foundation. This is all about making sure the system is physically tough enough to survive in the sky. This is what we call environmental hardening, and it's all laid out in a standard called DO-160G. It means you have to prove, through testing, that this system can handle the insane, constant vibrations from rotors, extreme temperature swings, and powerful electromagnetic interference from something like a lightning strike, all without even blinking. All right, moving up a layer. We have our tough physical foundation, so now we build the brains on top, the logical core. And the guiding principle here is really simple. Eliminate every single point of failure. Absolutely none are allowed. So how do we do that? Redundancy. Lots and lots of it. Take a look at this 4x architecture. You basically have 4 independent brains. If one of them fails, no problem. The other 3 take over. If a second one fails, the system can still operate safely. The whole point is that no single broken wire or fried processor can ever take down the whole system. That's fail-operational in action. And that brings us to the very top of the pyramid, the apex. This is our final line of defense, and it's designed to stop the one thing that keeps every battery engineer up at night: a thermal runaway, a fire. The system has to prove, and I mean physically prove it, that if one single battery cell has a catastrophic failure and catches fire, that fire will stay put. It absolutely cannot spread to the cells next to it. We call this non-propagation. It's the ultimate safety net. It means even if the worst thing happens in one tiny spot, the rest of the battery pack keeps on working, giving the pilot plenty of power to land safely. Okay, so we've built our pyramid. It's tough, it's redundant, it's safe. Now let's look inside the brain itself, at the advanced algorithms that are making these life or death calculations every single millisecond of a flight. The BMS is constantly juggling 3 critical numbers. We often call them the state of X metrics. First is state of charge, or SOC. That's your fuel gauge. Simple enough. Second is state of health, SOH. That's tracking the battery's long-term wear and tear. But the most critical one for an aircraft is state of power, or SOP. This tells the pilot exactly how much power is available right now. Now, here's where it gets really fascinating. To calculate those numbers accurately, you have to measure every single cell in the battery pack, and there can be hundreds of them, at the exact same microsecond. Look at that top graph. When the timing is just a tiny bit off, you get these phantom errors. But on the bottom, with what we call synchronous sampling, you get a perfect, accurate sum. In a car, that small error might not be a big deal. In the air, that error is the difference between knowing your limits and just guessing. So the big question is, when does all this crazy microsecond precision really matter? What's the one moment in flight where this becomes the absolute difference between safety and disaster? Well, it all comes together in this ultimate stress test, the balked landing. Just picture it. The aircraft is on its final approach to a rooftop helipad. The mission's almost over, the battery is low, and then suddenly the landing zone is blocked. You have to abort. You have to punch it and go around right now. That maneuver demands an immediate, massive surge of power from a battery that's already depleted, probably has some age on it, and might even be cold. The BMS's ability to have accurately predicted the state of power for this exact moment, that is the system's final exam. If it got that calculation wrong, the aircraft simply might not have the power it needs to climb away. So when you put all of this together, this incredible intelligence, the redundancy, the entire safety architecture, it leads us to a really powerful conclusion.
An eVTOL's battery management system isn't just a glorified battery monitor, not even close. When you look at a hybrid system like this P13 architecture, you can see the BMS is the central nervous system of the entire aircraft. It's coordinating huge amounts of power between generators, motors, and the battery itself. It's a flight-critical piece of avionics, plain and simple.
And that is why we have to see this as a complete revolution in thinking, not just an evolution of what's in our cars. This is what happens when you take the unyielding, top-down principles of aerospace safety and apply them to every circuit, every algorithm, and every single line of code. It really leaves you with a final thought. What other technologies are going to need this same revolutionary leap as we continue to electrify our world?